Hi everyone, thanks for checking out this video. So this is going to be a lesson about how to linearize around an equilibrium point for a nonlinear system of ODEs. And I'm going to be using the Predator-Prey model for an example. So we're basically going to be finding the equilibrium points and then picking one of those points and then linearizing the system around it. So you guys might be thinking right now, like, if this sounds like kind of a complicated topic, so why do I have a bunch of like 8th grade, like, simple stuff on the board? Like, this looks like way too simple to be about, like, linearizing around some kind of nonlinear ODEs, right? I mean, it's just, like, way too simple. Well, the reason I have this on the board right now is that before I show you guys how to do this for a system of ODEs, I'm going to just do a quick review of how we would linearize around a point for, like, a regular curve. And then the idea is that even though when we do the system of ODEs, it's going to look a lot more complicated because it's going to have like matrices and like linear algebra and stuff. It's going to look a lot more complicated with the notation, but what we're actually going to be doing is basically the same concept as just linearizing around the point of like a regular curve. So yeah, before we get into the ODEs and stuff, let's just like quickly solve this problem. So let's say we have this like the simplest ever parabola. So it's y equals x squared, just like totally basic parabola curve there. And let's say we want to linearize, or let's just say we want to find the tangent line that touches this point 1, 1. So if you guys remember, the tangent line is just the line that like, it's the line's going and it like touches the curve at this point, but doesn't cross it. So it's just going and it touches it only this point and then keeps going. Yes, let's just solve this problem, and this is going to be like an easy problem, but then you guys are going to see that like linearizing around the predator-prey model is just going to be kind of basically doing the same thing, just with like more complicated like matrix notation. Okay, so the way we do this is with this like point slope formula. So we have our point we want to linearize around, just 1, 1, and the y1 and x1 here, these are the coordinates for our point. And then we have y and x, those are just the variables, and then m is our slope. So you guys might remember this formula from like 7th or 8th grade or something. It's like very, very basic like way of writing a line. So I just want to show you guys like another way of writing this, like without really changing anything. So I'm basically just gonna move this term y1 over here. So I'm going to say y equals m times x minus x1 plus y1. So the only reason I'm moving this over to this side is just when we get to the predator-prey model linearization, the formula that we're going to use is going to look a lot like this. It's going to look a lot like this, except it's going to be in like matrix linear algebra notation. But yeah, okay. So let's just start plugging in things here. So we have y equals m. We'll get to solving for the m in a second. X minus x1 is 1, so x minus 1, plus y1 is also 1. That's our point here. Now, how do we find the m? So the m is just the slope at this point on the curve. And if you guys remember some like basic calculus, the way we find the slope on a curve at a given point is by taking the derivative. So again, like pretty basic stuff here. So I'm just going to take the derivative of this. So the derivative I'm going to call y prime is just going to be 2x. So hopefully you guys remember how to get this derivative, kind of just some like very, very basic calculus here. And then so if we want to find the slope of the curve at this point 1, 1, we just plug in 1 for x here. Yeah, so the slope is just going to be 2, right? So you guys see, I just plugged in x as 1 here, and then that gives us the slope, which is 2 times 1, which is 2. Okay, so now we just plug in the slope of 2 for our m, and then we have y equals 2 times x minus 1 plus 1, and then let's just multiply this out. 2x minus 2 plus 1, and then our final answer is going to be y equals 2x minus 1. And so this here is the slope for this, the equation for this tangent line. So I'll just write y equals 2x minus 1. So super easy, right? So maybe you guys remember this from like high school or like middle school or something. Probably not middle school because you had to take a derivative, but maybe like high school or something. So yeah, super easy. But you guys are going to see that next we're going to do this for the system of ODEs. And you guys are going to see that it's going to be basically the same idea with just a little bit more complicated notation, but basically the same concept of just, yes, we're basically just going to have a formula. It's going to be a lot like this, and we're just going to again plug things in and just solve it. Okay, yes, let's just get to the actual predator-prey model now. Okay, guys, so here's the basic predator-prey model. It's just a model with two variables, x and y. And the x is the prey, so I'm just calling the x fish for like an example. And the y is the predators, so I'm calling this like bears for an example, because bears eat fish. But it could be any system of like predators and prey, or it could even be like more of an abstract thing like a bacterial system or something. But yeah, just for example, I'm going to talk about like fish for the prey and then bears for the predators. And then we have these two ODEs here. Also quick note on the notation. So what I've written here, this x dot and y dot, this is just another way of writing the derivative with respect to time. So I'll just note here, this is the same thing as saying dx dt and dy dt. These are just the derivatives with respect to time. Just an easier way of writing those. So the equation for the prey, we basically have like a reproduction term for the prey. So we have a, which is a constant parameter, times our variable x. That's just the rate at which the prey population is growing, and it depends on the current level of the population. And then the prey species is also dying off with this term here. So we have a constant parameter b, and then the death rate for the prey also depends on the current level of the predator population, because the thing that's killing off the prey is being eaten by the predators. So that's why we also have y in this death term here, because this death term depends both on the current level of the prey population and on the current level of the predator population. And then, yeah, we have this constant parameter b. So then for the predators, we have their population growth term, and we have a constant parameter c. But then the growth term also depends on the current level of the prey population. That's why we have an x in here, because for the predator population to be growing, they need to be getting enough to eat. They need to be getting some of these fish to eat for the bear population to be growing. And then we have the death term for the predators here, constant parameter h. Instead of d, I made it h so we don't get confused with the derivative notation. But yeah, h is just a constant parameter here. And then this depends on the current level of the predator population. Okay, so the first thing to do before we start doing any kind of linearizing or anything is we need to actually just find what the equilibrium points are. So if you guys remember, when we have the system of ODEs, the ODEs are basically measuring change in the variables. That's what a differential equation is. It's a measurement of change of one variable with respect to another variable. And so these are just measuring the changes in the variables with respect to time. It's like dy dt, measuring the change in y with respect to the change in time. So the way we find an equilibrium point for a differential equation is by setting the equation to 0, because when we set these equations to 0, that means that no change is happening in the system. Because if the derivative is 0, that means there's no change happening. So let's just do this and get started. So we'll set this one equal to 0. So we'll have 0 equals ax minus bxy. Just move this over to the other side. bxy equals ax. Divide both sides by x. So by equals a, and then y equals ab. Okay, I'll just, since this is like an equilibrium point, I'll just call this like y hat. You might see it called like y star or something. I'll just call it like y hat for now. So we need to also find our value for x too. So we'll do this by setting the second differential equation equal to 0. So we'll just say 0 equals cxy minus hy. Move this over to the other side. So we have hy equals cxy. Divide both sides by y. So we have h equals cx. And then x equals hc. Again, I'll call this x hat. So this is our non-trivial equilibrium point. X equals h over c and y equals a over b. You guys might have noticed that we also have a trivial equilibrium point of 0, 0, because if both x and y are equal to 0, then these differential equations will also be equal to 0. But that's a trivial point because, like, of course, if in this model, if we don't have any of either species, of course that's going to be an equilibrium. But that's kind of not really what we're interested in. But I'll note it here just to have it for completeness. I'll put 0, 0. So yeah, one of them is 0, 0, and then the other one is h over c and a over b. Okay, so these are our equilibrium points. Yeah, again, it's pretty easy. We just set these equations equal to 0 and then solved for our variables. Yeah, so for the next step, let's try to linearize the system around this non-trivial equilibrium point. Okay, guys, so this is going to be the part where things start to look a bit more complicated because we're going to be basically putting everything in matrices to just make the system easier to work with. So it's going to start looking more complicated in terms of notation, but I'm going to try to explain how the formula we're going to be like trying to plug stuff into is basically going to be like conceptually the same as the point slope formula that we worked with at the start of the video. Okay, so let's just try to like put some of these things in matrices to just get them like easy to work with. So we're going to find a matrix called A, which is just going to be our two variables, x and y. So just a column matrix like that, one column, two rows, x and y, just basically just putting our variables in here. And then we're going to define the differential equation matrix, just A dot. And this is just going to be our differential equations, x dot and y dot. And remember, this notation here, the dots, all it means is the differential equation, which is just the derivative of the variable with respect to time. So x dot is just the derivative of x with respect to time. So it's just our equation for the the differential equation here. So yeah, these are our differential equations. If we want, we could even plug the entire thing in there. We could just write it like the whole equation instead of writing x dot. So if you ever like get confused or something, you can always like reason your way, reason back to things making sense by just plugging in the whole equation if you have to. And then the next one is going to be a hat, which is going to be our equilibrium point that we're linearizing around. So this is going to be x hat, which is h over c. And then y hat. which is A over B. So this is just our equilibrium point. Okay, so we're just going to be putting these things into matrices to just make them easier to work with. But if you guys ever get confused, you can always just like plug in the original things back into these matrices and kind of work it out that way if you have to. Okay, so the formula we're going to be using looks a little bit scary. So just to like ease you guys into it, I'm just going to write down the simple like point slope formula again and just remind you guys of this really quickly. So the point slope formula is just y minus y1 equals m, the slope, times x minus x1, right? So x1 and y1 are just the points, these are just the coordinates of the point that we're linearizing around. And then we have m, which is our slope, and then x and y are our variables, right? Okay, so now I'm going to show you guys the formula that we're going to be using to linearize around our ODE system. Okay, so just bear with me here, because I know it looks scary, but it's not that bad. Trust me. Okay. A dot equals. Sorry, I should put like an A dot L equals. Okay, so here it is. I told you guys it was pretty scary looking, right? So I know it looks very intimidating, but I'm gonna like quickly explain what all these things are and how all of them correspond to some term in our like simple point slope formula. And then after that, we'll start plugging things into it. Okay, so this whole thing is going to give us an equation, or sorry, a system of equations that are linearized. So I just put like the solution we're looking for is going to be like A dot sub L. I'm just writing sub L because this is going to be like a system of differential equations that is related. It's related to this original ODE system, but it's going to be linearized around this equilibrium point. So this is just what we're trying to solve for here. A dot sub L. This is going to be our system of linear equations. Okay, so we have this term here. Looks confusing, right? What is this like upside down triangle? This is just the gradient term. It's what's called gradient. So the gradient is going to be a matrix of partial derivatives that describe how the variables are changing with respect to themselves and like every other variable. So once we start plugging things in the next step, this is going to hopefully make more sense. But this is just like the gradient that describes how all the variables are changing with respect to themselves and each other. So this is basically like the slope term here, because it's basically like the slope in our point slope formula is describing the change of the function with respect to the variable. The gradient is just like the slope of the entire system of differential equations. So, and just like we want to find the slope at our fixed point in the point slope model, we wanted the slope at that one point that we were solving around. We're also going to be finding the gradient evaluated at our equilibrium point. So yeah, this whole thing here, this is just like the M term. It's just the gradient, which is like the slope, but for a whole system of ODEs evaluated at our equilibrium point. And then this part here is just our variable matrix minus our equilibrium point matrix. Again, that's similar to just x minus our x coordinate. Again, it looks exactly the same as this. And then this term over here, it's basically, remember in the beginning of the video, I showed you guys how we can just move this y coordinate over to the other side. Just put it over here. That is what this is. This is just the system of ODEs, like the solution to that system of ODEs at our equilibrium point, which we kind of know is going to be 0 already because we found the equilibrium point by setting these ODEs equal to 0. So we already kind of know that this is going to be 0, but I'll show you guys how to like plug things in and solve for it in case you wanted to solve around a point where it wasn't equal to 0. But yeah, so I hope you guys are kind of following me. At this point, I know it looks complicated, but again, like I just explained, like everything in here corresponds to something um, in the point slope formula. Um, but yeah, so for the next part, we're going to start actually like plugging some things in and solving for all of these different terms. Okay, guys. So the next part is unfortunately too hard for me to do on the whiteboard, just because it takes up too much space and it's going to be too much kind of like doing algebra and stuff. So for this part, I figured it would actually just be simpler and easier to just make a LaTeX file. So I'm going to kind of walk you guys through how to plug everything in this LaTeX file I made. And this file will also be up on my GitHub if you guys want to download it and like take a look at it yourself. But yeah, so I started just with kind of explaining the basics that I showed you guys on the board already. So we have our system of ODEs here. X is the prey and Y is the predators. And then yeah, I repeated what we already did, like solving for the non-trivial equilibrium point. And then again, like putting everything in matrices. I just said here, like warning, like linear algebra ahead. I'm only kidding about that though. I'm not trying to like, yeah, I don't want to like scare you guys off. I mean, it's actually at this point, it's basically just going to be plugging things in, so it's actually not even like going to be that complicated or difficult. So yeah, this is the formula that I wrote on the board. All we have to do at this point is plug in things to fill out the terms of this formula. And again, I just want to remind you guys, like I said, it's kind of the same thing as this point slope formula. Okay, so let's just start plugging things in. I mean, this is all we have to do at this point is, even though it looks complicated, all we have to do is plug things in for these terms here. Okay, so the easy one to start with is going to be this term here on the end. So I wrote like f of a hat. All this means is this is just the solution to our original system of ODEs at our equilibrium point. So we actually already know this is going to be 0 because the way we found the equilibrium point was by setting the ODEs equal to 0 and then solving. So we actually already know this is going to be 0. Kind of like, sorry for the bad handwriting, but I'll kind of write this here. So we know there's going to be 0, but just to show you guys how it would be done if you have like another point where it's not 0, I'll show you guys how to do it and kind of prove it to ourselves that in our case it is 0. So yeah, like I said, all we're doing to find this term here is we're just taking our original system of ODEs, here, and all we're going to do is plug in our equilibrium points. So we're plugging in our x hat and y hat values into this system of ODEs here. So when we do that, we get, all I did here is just change x and y to x hat and y hat. And if you remember, x hat is equal to h over c, and y hat is equal to a over b. So I just say, okay, this is equal to our ODEs with these x hat and y hat equilibrium values plugged in. And then I just plug in the actual values in terms of the parameters for these equilibrium values. So this becomes, instead of a times x hat, it becomes a times h over c. Remember, this is just what x hat is equal to. And then y hat is a over b. And then from here, we just crunch these numbers and just compute out the algebra here. And then, I mean, you can do this on paper if you want to, but if you just solve out these equations, you get 0 for both of them. Sorry, this is actually a small mistake here. This actually should be not 0 as a scalar, but actually 0 as like a matrix. So sorry about that, like slight notation mistake. But yes, it's not 0 as a scalar. It's 0 as a matrix here. Yeah, I'll change that before putting it on GitHub. But yeah, so this is just 0. Whoops, actually should be the same thing here. But yeah, you guys get the idea. I mean, the idea here is just basically that we can ignore we can ignore this f of a hat term, right? Okay. So the next thing we're going to do, after we now know that we can just eliminate this. This is just going to be like a matrix of zeros. We can just eliminate this from our formula, and we just proved to ourselves why. But just so you guys remember, I mean, you may be doing this for another point where this is not equal to zero. If you choose an equilibrium point, it will be equal to zero. But if you choose a non-equilibrium point, this might be equal to something else. So you may need to pay attention if you're solving around like a non-equilibrium point. Yeah, so the next one is going to be a little bit more complicated. So this next term here, it looks complicated with the notation. It's the gradient of our original system of ODEs evaluated at our equilibrium point. So that's this term here. I know it looks complicated, but it's just saying the gradient evaluated at our equilibrium point a equals a hat. I know it's kind of small. Oh, sorry for all these notation mistakes. Yeah, this should actually be a dot here because it's our gradient of our original system of ODEs. So yeah, again, sorry about like small notation mistakes. I'll change that before I upload it. But yeah, so basically, this is what the gradient actually is. So this is what the actual matrix is that we're talking about. It's just the partial derivatives of our original equations we were talking about. So the partial derivatives with respect to the original variables. So we have like this term here is the partial derivative of x dot with respect to x. And then we have our partial derivative of x dot with respect to y, and then partial derivative of y dot with respect to x, and then partial derivative of y dot with respect to y. Again, sorry about the notation mistake should be x dot here. Sorry about that. But yeah, so again, I know it looks complicated, but I'm just going to show you guys like how we would actually like fill out this matrix in terms of the parameters like we have it here. So, okay, let's just start with like the first one. Partial derivative of x dot with respect to x. So we just go back to our original x dot equation. Remember, this is the original derivative of x with respect to time. So in order to get the partial derivative for our gradient here, we're just going to take the derivative of this equation with respect to x. So when we take the derivative with respect to x, we get, let's see, a minus by. So I just hopefully you guys remember how to take a derivative from your like intro to calculus class. So yeah, it should be a minus by, right? Yeah, okay. So we just plug that in here. Then we do the same thing, except we take the derivative with respect to y. So that should be negative bx, right? Taking the derivative of x dot with respect to y, right? Negative bx. So we just plug that in here. And then we're going to do our derivative of y dot with respect to x. So we go up here, we have our equation for y dot, and we're going to take the derivative of this equation with respect to x, right? So it should be cy, right? Again, I'm hoping you guys remember how to like take a like simple derivative like this. But yeah, cy, just plug that into our gradient matrix here. And then yeah, for the last one, derivative of y dot with respect to y. Yeah, so we just take the derivative of this equation with respect to y. So this should be cx minus h, right? Right, cx minus h. Okay, so at this point we've solved for the gradient, but we don't just want the gradient, we want the gradient evaluated at our equilibrium point. So we need to plug in here our x hat and y hat for our equilibrium point points. So basically we just like, this is our gradient, but we next need the gradient evaluated at our x hat and y hat point. Sorry, again, this slight notation mistake here should be a dot. But yeah, so basically we're just going to take this and we're just going to plug in our x hat and y hat values. Just plugging this into our gradient matrix. We're just going to take all these x's and y's and plug in x hat and y hat. So I've done that here. And then remember, we have our x hat and y hat in terms of the constant parameters. So yeah, y hat is equal to a over b, and x hat is equal to h over c. So what I do next is, after just changing these x's and y's to x hat and y hat, I next just plug in the actual values of x hat and y hat in terms of the constant parameters. So just plug in h over c for x hat and a over b for y hat. And then from here, we can just compute out these terms. So we can just compute out a minus b times a over b. We just get 0 for that. And yeah, just for each of these terms, just compute them out, and then we get this final answer here, which is the whole term. Like this whole term, the gradient of our system of ODEs evaluated at our equilibrium point. This whole term, we've solved it out step by step into this matrix here. This is just the gradient of our system of ODEs. We found our gradient, and then we plugged in our equilibrium points, x hat and y hat, and then we just computed it out to see that it's equal to this matrix here. So I hope you guys are still following me. I don't think we've done anything like too difficult at this point. Again, it's like I said, a lot of computing out the algebra and stuff, but it's really just a matter of like plugging things into this formula. So okay, now we've plugged in. We found that this last term is just nothing. It's just a 0 matrix. So we just ignore this last term. We've solved for this whole term here. We've gotten this matrix. And then so there's only one more thing we really need to solve for. So the next thing is just this a minus a hat term. This is going to be the last thing we need to plug something in for, and then we're going to be in good shape to start actually like writing down our linearized system of equations. So almost done. Hope you guys are still bearing with me here. So a minus a hat. So the best way to do this is to just like substitute in the actual things that are in these matrices, I think. So a minus a hat really is just this xy matrix minus this x hat y hat matrix. Okay, so all we have here is just our xy matrix minus the x hat y hat matrix. So that's equal to we can just write the matrix another way. We can just combine them together. Again, just some matrix arithmetic. Maybe you guys remember from like your linear algebra class. Yeah, if we have like the subtraction of matrices, we can just write that as like element-wise subtraction. So this subtraction of these two matrices is just equal to the matrix, the column matrix x minus x hat and y minus y hat. And then, so lastly, we just plug in, again, our x hat and y hat values here. So this becomes x minus hc, and then y minus ab. Again, just plugging in hc for x hat, and then ab for y hat. Okay, so at this point, we've figured out what we're going to be plugging in for all of our terms. So yeah, again, we're plugging in nothing for this last term here because this is just equal to 0. And then we have a matrix we're going to be plugging in for this gradient term here. And then we have like a column matrix we're going to be plugging in for this term here. Okay, so after plugging everything in, we just plug in this matrix we found for our gradient evaluated at the equilibrium point. That's just going to be this 2x2 matrix here. And then for this term here, we're just plugging in this column, this one column 2 row matrix that we just found here. Okay, so just to remind you guys, like this term A sub L dot, this is just what I'm writing to describe the linearized system of ODEs that we're trying to solve for. So from here, we plugged in everything we need to plug in. Now it's just a matter of doing the actual like matrix multiplication. Again, I hope you guys remember from your linear algebra class like how to do a matrix multiplication. But yeah, we basically just have to like multiply these out, and then we just get this answer here. So yeah, just multiplying these two matrices out, we just come up with this product matrix. Again, I hope you guys remember how to multiply matrices. I'm going to kind of like skip over like the number crunching for now. So hope you guys remember how to do that. But yeah, so this at this point, this is basically our answer, and at this point we can unpack this this matrix to get our actual system of linearized ODEs here. So yeah, this is the answer. Like this is what we have for our linearized system of ODEs. And again, we just got that by plugging these things in and then multiplying out these matrices. So yeah, I mean, this is it. You guys can stop here if you want. I mean, this is the answer to the original question we had of how do we find a linearized system of ODEs, linearizing around an equilibrium point for our original non-system of ODEs. We have answered that question just by, again, plugging things in and then like multiplying out these matrices here. This is our answer. But if you guys want to go a step further, you can try to like repackage this linearized system of ODEs into this nice like matrix format if you want to. So again, like this here, this is the answer. Like we can just, if we want to, we can stop here and we've successfully found a linear system of differential equations around an equilibrium point of the nonlinear differential equations. But I'll show you guys one more thing. So I'll show you guys if you want to get it back in this format, like a lot of times you see like linear equations especially being written in this kind of matrix format, like A dot equals X dot equals, sorry, horrible handwriting, but yeah, a lot of times you guys will see linear systems of equations written in this kind of format where you have like X dot equals like A, which is some matrix, X plus B, which is like a column matrix. If you guys choose to go a step further and you want to like write your solution in this form, then I'll show you guys quickly how to do that too. So basically we just need to like find these question mark matrices that we can plug in so that if we multiply them out, we'll end up with this answer. So we should be able to kind of get these, like if we've done everything correctly, we should be able to kind of get these from our answers that we've gotten up here. So this this addition matrix that we're adding at the end, this is just going to be it's just going to be these terms here for the system we're working with. So we're going to put these like right down here in this addition matrix. And then these terms here, like this matrix here is going to be this matrix from up here, like before we multiplied it out. And we're able to do this in this case because we don't have to worry about this like extra like this, you know, that extra term we had that was just it was just zero, like evaluating at the equilibrium point. We don't have to actually worry about that. Sorry, I'm not going to write the whole thing just because it's tough to it's tough to write like this. But yeah, this whole thing was just zero, so we don't have to worry about that. So if we want to get things back in this like nice form, all we have to do is take these like addition and subtraction terms that should be in terms of like, hopefully should be in terms of like only the constant parameters. We just put these down here, and then we take this like this matrix here, and we put that as our multiplication matrix, and then we have our linearized differential equations, and then the variable is here. And then if we've done this all correctly, we should be able to multiply and do like the matrix arithmetic here, like multiply out these two matrices and then add on this this column matrix here, and then we should be able to, from this notation, we should be able to recover the solution in this form that we found here. Yeah, so that's all I have for you guys for today. I guess I'll just note that from this point, once you have it in this like nice like linear, this nice like linearized form, you can do further analysis from here. Like you could do like a stability analysis by like taking the finding the eigenvalues of this 2x2 matrix. Could do like a stability analysis. For now, I'm not going to do that because if you do the stability analysis for this system, you actually get kind of like a messy result. So it's actually not that good of an example to teach on, although maybe I'll do it in the future. But yeah, if you want to, you could do like a stability analysis. And basically just having it in linear form is just like easier to analyze. But yeah, if you're trying to do this, like learn how to do it for like a homework problem or an exam problem, then yeah, probably this answer here is what's okay to stop at. I mean, this is like the answer to the linearized form of the ODEs. Okay, so yeah, that's all I have for you guys for today. So just let me know in the comments if you have any questions. I'll put this LaTeX file up on my GitHub if you guys want to download and take a look. But yeah, hopefully this all made sense to you guys. If not, like let me know any questions you have. But yeah, thanks for watching and see you guys next time.